Okay, let me show you some proofs using Pythagorean identities. The first one I have on the board here doesn't look like it should involve any Pythagorean identities. 1 minus cos over sine. This is somehow equal to sine over 1 plus cos. But as we get into it and we use some of the strategies from the other day, you'll see the Pythagorean identities show up. So yesterday, or the other video I showed you about Pythagorean or about identities, is that when I'm trying to prove identities, I try to change things to sine and cos, and I try to get a common denominator. This is one of those ones where we need a common denominator. So this side has a denominator of sine, and this one has a denominator of 1 plus cos. So what I'm going to do is multiply the expression on the left side by 1 plus cos over 1 plus cos. And on the right side, I'm going to multiply the expression by sine over sine. That way, I can get the same denominator on both sides. When I multiply over here, I get sine times 1 plus cos on the bottom. In the numerator, when I multiply, I get 1 times 1, which is 1. I get negative cos. I get positive cos. And I get minus cos squared. On the right side, I end up with sine squared. And on the bottom, sine times 1 plus cos. The denominators are the same, so somehow I have to get the numerators to be the same. If I look carefully at this, positive cos, subtract cos, those cancel, so I get 1 minus cos squared over sine 1 plus cos. And if I look at the two sides now, I just have to remember that, oh yeah, since sine squared plus cos squared is 1, 1 minus cos squared is really just sine squared. And then the two sides, the left side and the right side, are actually equal to each other, and I've proven that identity. I can't just multiply things across. I can't cross multiply here to prove an identity. I have to keep each side separate, working at getting a common denominator to show that they're actually the same thing. Okay, let me try another one here. Sine to the fourth minus cos to the fourth is somehow equal to sine squared minus cos squared. All right. So on this one, everything's in terms of sine and cos. There's no common denominator, so the only thing I can do is make use of Pythagorean identities. But before I do that, I somehow have to get my to the fourth to be squared. And so what I have to remember is some math 10 and math 20 factoring, difference of squares. So if you have x squared minus 9, it factors into x plus 3 times x minus 3. And we can just take the square root of each of the terms when we have two terms that are square expressions and we're subtracting. It's called a difference of squares. So on this one, what we're going to do is take the square root of each of these. So the square root of sine to the fourth is sine squared. And the square root of cos to the fourth is cos squared. One of my factors is going to be those two added, and the other one, those two subtracted. Now, once I do that, hopefully I catch that sine squared plus cos squared is 1. And then I just have sine squared minus cos squared on this side, which is exactly equal to the right side. So it's that simple. So sometimes they can turn out to be quite simple, even though they look really complicated, and the factoring can be a little bit tricky for sure. All right, let's try another one here. Sine x minus cos x squared. Somehow that's going to be 1 minus 2 sine x cos x. So here I can't use the Pythagorean identity to start with because the square is acting on the whole thing. I actually have to realize that this really means sine minus cos times sine minus cos. And then I can actually multiply this out. Sine times sine is sine squared. Whoops, got to put the squared in the right spot. Sine times negative cos is negative sine cos. Sine times negative cos times sine is again negative sine cos. And then negative cos times negative cos is positive cos squared. And again, I end up with sine squared plus cos squared, which is just 1. And then I have a sine cos and another sine cos, both of them being negative. And the two sides are equal. So using some of these Pythagorean identities help us to prove, can help us prove some of these trig identities that we're trying to solve for.